You lost a piece of your day in 2025 and no one told you. On 9 July 2025, Earth spun a little faster than normal and the full rotation came up short by about 1.3 to 1.6 milliseconds compared to the standard 86,400 seconds we call one day. You woke up, checked your notifications, went through your routine, and the clocks quietly recorded that this particular day was one of the shortest ever measured. You didn't feel any jolts, nothing looked different in the sky, but from the point of view of precise timekeeping, the planet ended that day early. But before we continue, please subscribe to the channel to give your support. Let's continue. If you never noticed it, how did anyone even realize this happened? The answer is atomic clocks. Around the world, national labs run clocks that do not care about sunrise or sunset. They measure time using the energy jumps of atoms, especially cesium and rubidium. These clocks count billions of identical ticks every second, far more stable than the rotation of Earth. When scientists compare Earth's rotation to these clocks, they can see tiny differences of microseconds, even smaller than a millisecond. So when the planet speeds up or slows down, it shows up as a mismatch between the sky and those devices sitting in underground labs. A millisecond sounds ridiculously small. 1 second is already quick. A thousandth of that feels like nothing. A full day has 86,400,000 milliseconds, so losing 1.5 is a change of about 1 part in 50 million. To your body, that is totally invisible. But in high-precision systems, you do not ignore 1 part in 50 million. Think of it this way. If you're trying to line up a satellite, an aircraft, and a ground antenna that are all moving, and the timing in your math is wrong by even a tiny fraction of a second, their positions don't match where your software thinks they are. At that point, tiny becomes expensive and dangerous. So why does this tiny missing slice of day matter so much for technology? Because a lot of modern systems treat time as the most important variable. GPS is the best example. GPS satellites orbit about 20,000 kilometers above Earth, moving at roughly 4 kilometers per second, around 2.5 miles per second. They broadcast very accurate time signals. Your phone listens to several of them, compares the arrival times, and solves for your position. If timing is off by 1 microsecond, that's a millionth of a second, the signal from a satellite will arrive about 300 meters, or about 1,000 feet earlier or later than expected. That's enough to put your location on the wrong side of a highway or in the wrong building. Now stretch that out to the full global system. GPS and its cousins in Europe, Russia, China, and elsewhere all assume that the relationship between Earth has rotated this much and the clock says this time can be modeled with very high accuracy. If the planet speeds up slightly day after day and you don't update the models, you introduce errors into navigation, surveying, and even the financial networks that use those signals to synchronize clocks in data centers. The change of a millisecond in day length won't crash civilization by itself, but it will quietly push more and more systems outside the safety margins they were designed for. Here's the next question. Was 9 July 2025 just a random oddball or part of a pattern? It turns out it was part of a pattern. The summer of 2025 had several days that came in shorter than usual, again by around 1.3 to 1.5 milliseconds. Dates like July 9th, July 22nd, and August 5th showed up in the rotation data as some of the shortest days since precise measurements began in the 1960s. Right before that, on 5 July 2024, Earth set an all-time speed record for the atomic clock era, with a day roughly 1.66 milliseconds shorter than the standard 24 hours. When you put those together, you don't see a random blip. You see a recent cluster of record-breaking fast days. Something in the way Earth rotates has clearly shifted on short timescales. If the changes are real, should you be scared, or is this just something for nerds in timing labs to argue about? Physically, this is not a doomsday scenario. You are not going to feel extra G-force at the equator, and you are not going to be thrown into space because Earth is spinning slightly faster. Jet lag, sleep cycles, and your sense of balance depend on light, hormones, and your inner ear, not on microsecond level changes in rotation rate. For your daily life, these millisecond shifts are basically invisible. That's why scientists are not terrified. They know the planet has always had small variations in rotation. So why are they nervous? Because the long-term trend, set mainly by the moon, goes the opposite way. The moon's gravity raises tides in the oceans. Water sloshing back and forth against continents causes friction, which slowly removes energy from Earth's rotation. Over centuries and millennia, that tidal friction lengthens the day by a couple of milliseconds per century. In plain language, Earth should very slowly spin down, not speed up. We have fossil and historical evidence that days used to be shorter hundreds of millions of years ago, and they've been stretching out over time. When modern data suddenly shows days that are shorter than the standard 86,400 seconds, it means some other processes inside the planet, in the oceans, in the atmosphere, or in how mass is distributed are temporarily overpowering the moon's braking effect. That breaks the smooth, slow change picture that many models rely on. This is where the stakes jump from theory to practice. Our official time system assumes that we can keep civil time, the thing on your phone and wall clock, closely tied to Earth's rotation with small corrections. The standard day of 86,400 seconds is a definition, but Earth does not care about definitions. It rotates how it wants. When that rotation starts drifting faster than expected, organizations that manage world time have to decide when to insert or remove leap seconds, how to keep satellite systems aligned, and how to guarantee that a second in New York means the same thing as a second in Tokyo. A millisecond here and there, repeated day after day, adds up to real offsets. And remember, the systems that care about this are not just telescopes and observatories. High-frequency trading networks stamp transactions with time down to microseconds or even nanoseconds. Communication networks and power grids rely on synchronized clocks to detect faults and coordinate switches. Military systems and deep space tracking stations depend on models of Earth's rotation that match reality extremely closely. When the planet quietly speeds up, every one of those systems has to check whether its assumptions still hold. Most people never hear about those meetings, but they happen, and they are serious. So the real point of that too short day in 2025 is not the lost 1.5 milliseconds you never felt. It is the signal that our 24-hour day is not a solid, unchanging unit. It is a moving target that depends on the complex physics of a rotating, fluid, layered planet. Now the key question becomes, how do we actually know the planet is speeding up, and not just seeing noise in our clocks? To answer that, you have to look at the long fight between the oldest timekeeper we have, the motion of the sun and stars, and the newest one, the atomic clock. That clash is where the mystery of Earth's faster spin really starts to sharpen. So how do you actually know Earth is speeding up, and it's not just one weird clock in a bunker going wrong? You have two completely different ways of telling time fighting each other. One is the sky, the old way, sunrise to sunrise. The other is a man-made system built on atoms, not on the sun. When those two drift apart, something in the planet's spin has changed, and that's exactly what we're seeing now. For most of history, a day meant noon to noon, or sunrise to sunrise. That's what scientists call universal time, UT1. It's just Earth's real rotation against the distant stars and the sun. If you only had sundials, you'd never know anything was wrong right now, because the sun still crosses the sky in about the same way. But today, the official second is not defined by the sun at all. It's defined by atomic physics. The International Standard Second is based on a very specific transition in the cesium-133 atom. A fixed number of those tiny oscillations is defined as exactly 1 second. Hundreds of ultra-stable atomic clocks in labs around the world tick away using that rule, and their combined output is called International Atomic Time, TAI. So you have UT1, how Earth is really rotating, and TAI, how our atomic clocks say time should pass. When those two stay in step, Earth is rotating at the rate we expect. When they drift apart, Earth is either running ahead or falling behind. That drift is not guessed, it's measured. Radio telescopes watching quasars, satellite tracking, and laser ranging tell us UT1. Atomic clocks tell us TAI. If Earth speeds up, UT1 pulls ahead of the atomic clocks. If Earth slows down, UT1 falls behind. Right now, the data shows the planet has been rotating slightly faster than the long-term trend predicts. But there's a problem. You don't live on TAI. Your phone and your laptop use something called Coordinated Universal Time, UTC. UTC is basically TAI with occasional tiny patches applied so that civil time stays close to Earth's rotation. That patch is the leap second. Since 1972, whenever Earth's rotation drifts enough that UT1 and UTC get more than about 0.9 seconds apart, timekeepers add one extra second to UTC, usually at the end of June or December. Every leap second we've used so far has been positive, meaning we've slowed the clocks down for 1 second so Earth can catch up. That fits the big picture. On average, because of tidal friction from the moon, the length of a day increases by roughly 1.4 to 1.7 milliseconds per century. Over decades and centuries, Earth is supposed to be coasting toward longer days. That's why leap seconds have only ever gone one way. We keep adding them to deal with a very slow spin down. So here's the paradox. From 2020 onward, the detailed records of Earth's rotation show a run of unusually short days. In 2020, 28 different days came in under the standard 86,400 seconds, making that year the champion for shortest days since precise atomic clock measurements started in the 1960s. Then, 29 June 2022 set a new record, with Earth finishing its rotation about 1.59 milliseconds early. Add to that the 2024 and 2025 record-breaking days we talked about earlier, and the pattern is clear. Instead of the slow, smooth lengthening you'd expect, Earth has been having spurts of faster rotation. That's when geophysicists and timekeeping experts started talking about something that has never happened before, a negative leap second. Instead of adding a second, you would remove one. Civil time would go 23:59:58, then skip 23:59:59, and jump straight to 00:00:00. The clocks would literally delete a second from the day. On paper, that sounds simple, but for software and hardware that quietly assume days sometimes get an extra second and that's it, this is a nightmare edge case. Logs, databases, satellites, financial trading systems, anything that relies on strictly ordered timestamps all have to handle a situation where a time that should exist simply doesn't. Many systems barely handle positive leap seconds without glitches. Almost none have been tested in the real world for a negative one. So how likely is this strange event? Recent analyses, looking at the post-2020 speedup and projecting forward, put the odds of needing a negative leap second in roughly the next decade or so at about 30%, assuming the current faster spin trend continues. That's not a certainty, but it's not negligible either. It's enough that people at national labs, GPS operators, and big exchanges are treating this as science fiction. They're actively modeling what their systems will do if sometime around the late 2020s or early 2030s, the international timescale suddenly has to drop a second. There's another twist. While all this discussion of a negative leap second is going on, the world's timekeeping authorities have basically decided that leap seconds themselves are too much trouble. In 2022, the General Conference on Weights and Measures passed a resolution to phase out leap seconds by or before 2035. The plan is to allow UT1 and UTC to drift farther apart than the current 0.9 second limit, maybe up to a minute or so over many decades, and then apply a much rarer, bigger correction instead of constantly fussing with single seconds. So Earth's recent speed-up is not just an interesting geophysics puzzle. It's one of the main reasons we're about to redesign how civil time works for the whole planet. Keeping clocks glued tightly to the sun with frequent leap seconds turned out to be fragile, especially in a digital world where every discontinuity in time can crash something. The planet's behavior forced timekeepers to admit that our patch system doesn't scale. So step back and look at what you've got here. On one side, there is the sky, giving you UT1, the raw rotation of Earth. On the other hand, there is a worldwide network of atomic clocks giving you TAI, and from that, UTC. For decades, we used leap seconds to keep them close. Then, Earth's rotation shifted just enough and just fast enough that people had to seriously consider deleting a second from UTC for the first time ever, while at the same time planning to scrap leap seconds altogether by 2035. That is how we know the planet is speeding up, in a real, measurable way. The disagreement between the clocks and the sky has grown big enough to bend the entire global time standard. And now the obvious question hits. If the long-term physics says tides and the moon should be slowing Earth down, why are we even in a situation where a negative leap second is on the table? What is powerful enough to temporarily override that braking and make our days shorter instead of longer? Earth is supposed to be slowing down, not speeding up. That's the basic problem. The normal physics story says the rotation of our planet should be calming down over time, like a spinning wheel slowly losing speed. But the data from the last few years shows the opposite trend on short timescales. If the brakes are always on, why are we suddenly seeing the system lurch forward? Start with the main brake, tides. The moon pulls on Earth's oceans and creates tidal bulges. Earth rotates once in about 24 hours, the moon orbits in about 27.3 days, so the bulges don't sit directly under the moon, they're dragged slightly ahead by Earth's faster spin. That offset plus friction between moving seawater and the seafloor constantly pulls on the planet's rotation. Energy gets drained from the spin and dumped into heat and into the moon's orbit. The result is simple. Over long times, days get longer. If you look at the numbers, the effect from tides alone increases the length of day by on the order of a couple of milliseconds per century. You're talking roughly a few 10,000ths of a second per year. That is tiny, but it does not stop. Every century, the planet's rotation stretches a little. Over millions of years, those tiny steps stack up into a completely different day length. That's the basic expectation. Slow, steady braking. How do we know this isn't just a theoretical story someone wrote down on a whiteboard? Because the history of Earth's rotation is literally recorded in rocks and fossils. Certain ancient corals and layered microbial structures called stromatolites grow in daily and seasonal cycles, leaving behind visible bands, a bit like tree rings but at a finer level. When scientists count those bands in fossils that are hundreds of millions of years old, they find something striking. There were more days in a year back then. In the late Paleozoic and Mesozoic, for example, some coral fossils show around 400 daily layers per year. The year itself, set by Earth's orbit around the sun, is basically the same length it is now. If you squeeze roughly the same year into about 400 rotations instead of 365, that means each day was shorter, on the order of 21 to 22 hours instead of 24. That's not a model, that's a measurement written into ancient biology. Lunar laser ranging backs this up from the other side. We bounce lasers off reflectors left on the moon and track its distance to millimeter precision. Those measurements show the moon is slowly drifting away from Earth by roughly 3.8 centimeters per year, roughly an inch and a half. That outward drift is the other half of the tidal story. As Earth loses rotational energy, the energy is transferred into the moon's orbital energy, and the orbit gradually widens. Days get longer, the month gets longer, and the system very slowly changes. Now, put that long, slow trend next to what we're seeing in the 2020s. On 5 July 2024 and several days in mid-2025, the length of day came in about 1.3 to 1.7 milliseconds shorter than the standard 86,400 seconds. That's not just below the long-term trend. That is below the nominal value we use to define one day in our time system. It's like the braking system that adds a couple of milliseconds per century just got partially canceled or briefly overwhelmed. To be clear, this does not erase the long-term tidal effect. Over millions of years, tides still win. But over years and decades, you can get oscillations on top of that slow drift. If in one specific year you see swings of more than a millisecond in day length compared to the standard value, you're effectively seeing a reversal of what tides do over centuries, compressed into a very short window. That tells you Earth's rotation isn't a smooth curve. It's a noisy signal that responds to multiple processes acting at once. So where is the extra spin coming from? This is where angular momentum bookkeeping shows up. There is a strict rule. In the absence of external torque, total angular momentum of the Earth system is conserved. If the solid Earth spins faster, you have to balance that with something else changing. Either you move mass around inside the system, or you apply external torques from gravity interactions with the moon and the sun. Inside the system, the easiest way to change rotation speed without adding or removing angular momentum is to redistribute mass. The atmosphere can speed up or slow down its winds. The oceans can shift currents and pile water closer to or farther from the rotation axis. Ice sheets can melt and move water from high latitudes toward the equator. Deep under all of that, the liquid outer core can change how it flows and how strongly it couples to the overlying mantle. All of those are ways of changing Earth's moment of inertia, the spread of its mass. For a fixed total angular momentum, if you move mass closer to the axis, rotation speeds up. If you move mass outward, it slows down. On top of that, you have external torques. The moon and the sun don't just raise simple tides. They apply gravity in complicated ways that can nudge Earth's rotation and orientation. The shape of Earth, the distribution of land and ocean, and the geometry of the moon's orbit all control how effective those torques are at any given time. Seasonal changes, long-period ocean and atmosphere patterns, and internal core dynamics get stacked together. When their contributions line up, you can get a net speed up or slowdown of a millisecond or two in day length on top of the slow tidal trend. So the puzzle isn't that Earth's rotation changes. Everyone in this field knows it does. The unsettling part is the size and timing of the recent changes. You have a long-term break-them tides that should be stretching days, you have clear fossil and lunar data confirming that slow trend, and then suddenly, in just a few years, you get a cluster of the shortest days ever measured in the atomic clock era. That means some combination of atmosphere, oceans, ice, and deep core flow has shifted strongly enough to show up directly in the length of day. The immediate consequence is that our prediction models are under pressure. The formulas and data sets that used to give decent forecasts of length of day years in advance now have to deal with anomalies at the millisecond level over just a few seasons. That's not enough to break your alarm clock, but it is enough to matter for satellite orbit predictions, precise pointing of telescopes, and the whole discussion about negative leap seconds. It's a sign that the Earth system is more dynamic and more tightly coupled across its different layers than older simplified models assumed. So the message here is blunt. By the basic tidal story, Earth's spin should be gradually calming down. Instead, in the last few years, we're measuring stretches where it speeds up just enough to scramble our expectations. That tension between what should happen and what is happening is why scientists are so focused on this right now. And if tides are not the only driver, the obvious next question is, which other parts of the system are jumping in, especially the one we can't see directly, buried thousands of kilometers under your feet? The moon is supposed to be the big break on Earth's spin. But right now, it's also helping set up some of the shortest days we've ever measured. That sounds backwards, because the standard story is tides slow us down. But when you look at how the moon moves and how the oceans respond, you see a second layer. Depending on the exact geometry of the orbit, the tidal forces that normally act like a drag can, on shorter timescales, line up with slightly faster days. Start with the usual picture. The moon's gravity pulls hardest on the side facing it and weakest on the far side, stretching the oceans into a pair of tidal bulges. Because Earth spins once in 24 hours while the moon takes about 27.3 days to go around us, those bulges don't sit perfectly underneath the moon. Friction between moving seawater and the seafloor keeps them a little ahead of the moon's position. That misalignment slowly drains energy from Earth's rotation and passes it to the moon's orbit, pushing the moon away and lengthening the day over millions of years. Here's the twist. The tidal forces are not fixed. They change as the moon's distance and tilt shift. Sometimes it's closer to Earth at perigee, and sometimes it's farther, at apogee. It's also tilted relative to Earth's equator. In 2025, the days that showed up as the shortest were clustered around times when the moon was near apogee and moving on a path strongly inclined to our equator. That combination changes where and how strongly tides act on different ocean basins and even on Earth's crust. So how can simply changing the moon's position in the sky shave off milliseconds from a day? Because the braking system is not uniform. When the moon's path is far from the equator, the tidal bulges shift north or south in latitude. That changes how efficiently the tides can grab onto Earth's rotation. In some configurations, the torque that normally acts like a clean brake becomes less effective at slowing the spin. And in others, the mass shifts can briefly favor a slightly faster rotation rate for the solid Earth relative to the fluid envelopes. You can think of it in mechanical terms. If you move the point where a brake presses on a spinning wheel closer to the axle or farther from it, you change how much leverage it has. The total force might be the same, but the effect on the wheel's speed is different. In the Earth-Moon system, the lever arm depends on the latitude and phase of the tides, which depend on the moon's distance and tilt. Numerical models that combine the moon's orbital data with realistic ocean tide simulations show that these geometric variations can account for a significant part of the 1 to 2 milliseconds shortening of the day seen in specific years. But tides are not just theoretical curves, they are massive, moving loads of water. Twice a day, tides lift and drop trillions of tons of seawater by 1 to 2 meters. 1 cubic kilometer of seawater has a mass of about 1 billion tons. When that kind of mass is shifted toward or away from the rotation axis, even by a few hundred kilometers, it changes Earth's moment of inertia. For a fixed amount of angular momentum, if you move mass closer to the axis, the spin speeds up. If you move mass outward, it slows down. In that sense, the oceans are a global transfer machine. They take angular momentum from the solid Earth, store it in currents and moving water, and then hand it back. When strong tides or large-scale currents pull water closer to the poles, they reduce the effective radius of the mass distribution, and Earth can spin a tiny bit faster. When more water is sitting near the equator, the opposite happens. This is the basic physics that makes a spinning object turn faster when it pulls weight inward, just scaled up to entire oceans and the full 12,700 kilometer or 7,900 mile diameter of the planet. If the moon can move that much mass around, why not just blame it all for what we've seen since 2020 and be done with it? Because when scientists plug the precise moon orbit and detailed ocean tide models into their calculations, they still cannot reproduce the full pattern of the recent speedup. The moon's gravity clearly matters, and the odd geometry of certain years helps explain part of the story, but there is a leftover piece that doesn't match what tides alone should do. Something else, probably deeper and harder to measure, is also changing the rotation. Even with the best lunar ephemerides, that is, highly accurate tables of the moon's position, and advanced numerical models of global tides, the observed acceleration in Earth's spin since around 2020 is too large and too structured to be fully explained by the lunar configuration and oceans alone. That points towards the interior. Changes in the flow of the liquid outer core and how it couples to the solid mantle can trade angular momentum with the crust. The moon is providing the regular beat, but the core seems to be adding its own variations on top of that. So is the moon slowing us down or speeding us up? Over the long term, millions of years, the answer is still clear. It is slowing the rotation. Tidal friction is not going away. And if you project its effect far into the future, you end up with days that are closer to 25 hours long. The moon will be farther away, the tides will be weaker, and Earth's spin will be more relaxed than it is today. On the scale of years to decades, though, the story looks very different. The exact way the moon's orbit lines up with Earth's tilt and continents can give you temporary bursts of faster spin, shaving milliseconds off certain days. Right now, you are seeing a rare overlap. Lunar geometry is favorable for shorter days at the same time that internal processes in the atmosphere, oceans, and the core are pushing in the same direction. The result is a set of record-fast days that are forcing us to pay attention. And that leads straight to the more uncomfortable question. If the moon's influence and the tides still don't fully explain what we're measuring, how much of this new behavior is coming from deep inside the planet and layers we can't see or touch? If the outer core is quietly changing its flow and handing angular momentum back and forth with the mantle, then every tiny jump in Earth's spin is also a clue about what the hidden heart of the planet is doing right now in your lifetime. Right now, the most likely suspect behind Earth's faster spin is something you will never see, touch, or drill into. Under your feet, far below the crust and the mantle, there is a moving, conducting metal ocean that can quietly hand angular momentum to the surface and change the length of your day by milliseconds without a single person at the surface feeling anything at all. That's the part that should bother you a little. The clock on the wall is being nudged by a machine you can't observe directly. Start with the structure. Go down about 2,900 kilometers, around 1,800 miles, and you hit the core mantle boundary. Above that, you have the solid mantle, a very hot but mostly rigid rock layer. Below that boundary, you hit the liquid outer core, made mostly of molten iron and nickel. Keep going inward another 2,200 kilometers or so, and you reach the solid inner core, a metal sphere about 1,220 kilometers in radius, roughly 3/4 the size of the moon. These three big layers, the mantle, the liquid outer core, and the solid inner core, do not have to rotate at exactly the same rate. We know this not because anyone has been there, but because of seismology. When big earthquakes happen, seismic waves pass through the planet and bounce around inside it. By looking at how long those waves take to travel along different paths, scientists can infer how fast different parts of the core are turning compared to the mantle and crust. Over the last few decades, this work has suggested that the inner core sometimes turns slightly faster than the rest of the Earth, a behavior called superrotation, and that other times lags behind. The differences are small, but they are real, and they change on timescales of years to decades. So the deep interior is not locked to the surface like a solid steel ball. It is more like a nested set of rotating shells, with the liquid outer core acting as a slippery layer between the inner core and the mantle. The key question then is, how hard do those shells push on each other? And can that push be strong enough to show up in the length of day? That brings you to core-mantle coupling. The liquid outer core flowing around generates Earth's magnetic field. That flow is not just a passive background. It interacts with the mantle both mechanically, where irregularities at the boundary can transmit stress, and electromagnetically, because the mantle is not a perfect insulator. Changes in the pattern of flow in the outer core can change how much torque is applied to the mantle and crust. When that torque changes, the rotation rate of the solid Earth can speed up or slow down by tiny amounts. On paper, the numbers seem small, fractions of a millisecond in day length, but those are exactly the scales we're talking about. Several studies over the past few decades have shown that decadal variations in length of day match changes inferred in core flow from magnetic field data. In simple terms, when the field changes in certain ways, length of day responds with a delay and an amplitude that fit a model where the core is transferring angular momentum to the mantle or taking some back. That means we already know the core is involved in long period wobbles of Earth's spin. Now look at the recent speedup, the 2020 to 2025 pattern. Researchers first try to explain it with the parts of the system we can observe directly: atmosphere and oceans. Those are big players. Seasonal wind changes and large-scale climate patterns can shift day length by tenths of a millisecond. When you combine atmospheric reanalysis data and ocean circulation models, you can explain a large chunk of the short-term wiggles in length of day. But when you subtract those known contributions from the observed signal in the last few years, you're left with a residual that doesn't go away. That leftover is where the core comes back in. Some geophysicists argue that to match the full shape of the length of day curve after 2020, you have to add a contribution from changing core flow. The idea is that the deep dynamo, the same system that maintains the magnetic field, has adjusted its circulation in a way that slightly changed the torque on the mantle. If that's correct, then the extra spin you see in the clock data is literally the core retuning the whole planet's rotation. You're not just watching weather or tides, you're seeing the signature of deep Earth dynamics written straight into the definition of a day. The scale of that change is easy to underestimate. Shortening the day by just 1 millisecond sounds like almost nothing, but in terms of rotational kinetic energy, it's a huge shift. You're talking on the order of 100 billion joules of energy difference, bound up in the spin of the planet. For comparison, a truly massive earthquake can release around 1/10 of the 18th joules. So changing the length of a day by a millisecond is like shuffling around the energy equivalent of many giant earthquakes, not in one violent burst, but smoothly spread throughout the whole globe. And yet, you feel none of it. There's no extra sway in buildings, no change in gravity you could notice with your body, no extra G at the equator. It's like changing the rotation speed of an aircraft carrier's propeller by a millionth. The ship does not suddenly lurch, but if your navigation system is trying to plot its position to within a few centimeters, that tiny change matters. For Earth, the navigation system is everything we use to track satellites, launch rockets, or sync financial transactions. Those systems are sensitive enough that a barely measurable tweak in the core's behavior can matter at the surface. The uncomfortable part is how indirect all of this is. We cannot send a probe into the core. We cannot lower a thermometer or a camera 3,000 kilometers down. Everything we know about the core comes from proxies. Seismic waves, lab experiments on metals at high pressure, and measurements of the changing magnetic field at the surface and in space. The recent speed up in Earth's rotation adds a new kind of proxy. It is the core showing up in time itself. The length of day becomes one more data stream that constrains what the core is allowed to be doing. But the picture is still messy. Different studies disagree on details, like whether the inner core is currently speeding ahead of the mantle, slowing down, or even reversing its relative drift on decadal timescales. The exact patterns of flow in the outer core are reconstructed from magnetic field changes with big uncertainties. Now we're adding the length of day anomalies on top of that and trying to make everything line up. If they don't, you have to admit that parts of your deep Earth model are wrong or incomplete. So when you hear that Earth's day has shortened by a millisecond, don't think rounding error. Think the invisible engine at the center of the planet just changed state enough that the entire crust, the oceans, the atmosphere, and every satellite orbiting above had to follow along, even if we barely notice at the surface. Whatever is going on down there is strange enough that it's pushing us to rebuild our models of the core mantle system, and by extension, our models of how stable we think Earth's rotation really is. And that raises the next question, which pulls the problem straight into the modern world. If the deep interior and the moon are both tugging on the clock, what about the changes we are driving ourselves up here at the surface by melting ice and moving water around the globe? How much of the planet's spin history over the next few decades is going to be written not just by geology, but by climate change and the way we use water? You're changing the climate, and the climate is quietly changing the length of your day. That sounds over the top, but it's literally true. By melting ice and moving water around the planet, we're pushing mass toward and away from the equator, and that feeds straight into how fast Earth spins. Start with the basic twist. Climate change doesn't just heat the air and raise sea level, it relocates huge amounts of mass. When the big ice sheets in Greenland and Antarctica melt, that water runs into the oceans and spreads out, mostly toward lower latitudes. That makes Earth's mass distribution a little wider around the equator, increasing its moment of inertia, the spread of mass around the spin axis. For the same total angular momentum, a larger moment of inertia means a slower rotation, so the day gets longer. This isn't a guess. Satellite gravity missions like GRACE and GRACE-FO have tracked changes in Earth's gravity field over the last few decades. From that, scientists can see ice mass disappearing from Greenland and Antarctica and watch how that mass redistribution has already nudged Earth's rotation rate and shifted its rotation axis. The effect is tiny in human terms, but it's measurable, and it's now part of serious timekeeping calculations. Then there's the motion of the spin axis itself. Earth doesn't spin around a perfectly fixed line. The point where the axis pokes through the crust near the North Pole and South Pole wanders by a few meters per year. This slow drift and wobble of the poles is called polar motion. One component of that motion, with a period of about 433 days and an amplitude of a few meters, is known as the Chandler wobble. For a long time, that wobble was treated as a mostly natural internal behavior of the Earth system. Now, newer studies show that human-driven changes in water storage, ice melt, groundwater pumping, reservoir filling, are feeding into it. Hydrology and cryosphere changes are shifting enough mass around that the path of the poles is being measurably bent. Some recent work even suggests that by 2100, continued ice loss and glacier melt could move the poles by more than 10 to 20 meters, several dozen feet compared to where they would have been without modern warming. That is climate change literally pushing the spin axis sideways. Here's where it gets even stranger for the timekeeping story. In early 2024, a paper in the journal Nature pulled all of this together and found a direct link to leap seconds. The study showed that melting polar ice has already slowed Earth's rotation enough to counteract some of the recent speed up from the core and other processes. In plain language, without human-driven ice melt, we'd be heading toward a negative leap second sooner. Because we are melting so much ice, moving so much water toward the equator, we're actually delaying that moment by a few years. So you're in a very weird timeline. Burning fossil fuels speeds up ice loss. That moves trillions of tons of water. That increases Earth's moment of inertia and slows the rotation just enough to push the date of a negative leap second further into the future. A global environmental crisis has become one of the terms in the equation that decides when the world's clocks may have to delete a second. Put all the main players together and you get a clear pattern with two competing regimes. In the short term, on scales of years to a couple of decades, lunar geometry and core dynamics are pushing toward faster rotation, shorter days, and the possibility of needing a negative leap second. That's the 2020-2025 story. The moon's current orbital configuration, plus changes in the liquid core and atmosphere-ocean system, drove day length below the standard 86,400 seconds on a record number of days. On medium to long-term scales, though, climate-driven mass redistribution is pushing the other way. Ice melt in Greenland and Antarctica, plus groundwater depletion and changes in large reservoirs, are moving mass toward the equator and slowing the rotation. Over the coming decades, that effect grows, and the same Nature study concludes it will likely delay the first negative leap second by roughly 3 years compared with a world without this extra ice loss. So you get a simple, uncomfortable summary. Right now, it's fast now, slow later. Short term, a combination of moon, core, atmosphere, and oceans is shaving milliseconds off some days. Longer term, climate change is loading the equator with water and dragging the rotation back down. You are living in the interference pattern of multiple planet-scale processes, all adding and subtracting angular momentum and changing the clock by microseconds and milliseconds. The faster spin signal we're dealing with in this decade may peak and then gradually get buried under the climate-driven slowing. So that's why those headlines about shortest day on record are more than trivia. Each record day is a snapshot of everything happening in the Earth system: core flow, tides, winds, currents, ice melt, groundwater, even big earthquakes. Climate change is not just in temperature graphs and sea level plots. It's in the tiny irregularities of day length, in the drift path of the poles, and in the parameters that satellite operators use to point antennas and calculate orbits. When timekeeping labs work out whether UT1 and UTC are drifting enough to need a leap second, they're indirectly folding climate physics into the decision. Mass loss from polar ice sheets, water pumped from aquifers, and heat stored in the oceans all change Earth's rotation just enough that it shows up in those calculations. A few microseconds here, a few microseconds there, and suddenly the timelines for a negative leap second shift by years. So the message hidden in those milliseconds is blunt. The same human activity that's raising sea level and shifting climate zones is now also part of the reason the official global time standard might change earlier or later. Your car's GPS, your bank's transaction log, and the guidance system for satellites depend on a planet whose spin is being tweaked not only by the moon and the core, but also by your emissions and water use. And if climate can do that, If just moving ice and water can register in the planet's spin at the millisecond level, there's an obvious follow-up. What about the other giant fluid layers we tend to forget about, the atmosphere and the oceans as moving masses, not just as weather and currents? Because if winds and currents start to shift in new patterns as the climate changes, they're going to push on the clock as well, and that is where the picture gets even tenser. You feel wind on your face and see waves on the ocean, but do you realize those same winds and currents are helping decide how long your day is? The atmosphere and oceans are not just background weather, they're giant moving flywheels that store and release angular momentum, and every time they shift, Earth's spin responds, even if you never notice it directly. Start with the air above you. Earth's atmosphere has a mass of roughly 5 billion kilograms. That is enough mass that when it starts moving east or west in a coordinated way, especially in the jet streams at mid-latitudes, the atmosphere itself is spinning a little faster around Earth's axis. To keep total angular momentum balanced, the solid Earth can respond by slowing down very slightly, and the day gets a bit longer. You see this in seasonal patterns. As seasons change, the average wind patterns shift, and you can measure the length of day changing by about half a millisecond over the year. That is a direct signal of air masses trading angular momentum with the solid planet. You don't feel it, your watch doesn't show it, but the global time series does. In other words, when the jet stream moves or strengthens, it's not just changing storms and temperatures, it's pushing on the rotation itself. If regular seasonal wind changes can move the clock by half a millisecond, what happens when the whole climate system swings into a strong global-scale pattern like El Niño or La Niña? Those are not just temperature anomalies in the Pacific, they're reorganizations of winds and currents across much of the planet. El Niño Southern Oscillation, ENSO, is the best example. In a strong El Niño, trade winds in the tropical Pacific weaken, warm water sloshes eastward, and the pattern of atmospheric circulation above it shifts. In La Niña, the opposite happens, with stronger trades and cooler water in the eastern Pacific. These changes don't just affect rainfall in a few countries, they rearrange where the atmosphere and the upper ocean are holding angular momentum. When scientists look back over decades of rotation data, they see length of day wobbling in step with ENSO. Strong El Niño events are linked with changes in day length on the order of a few tenths of a millisecond. It's not a one-to-one mapping, because other processes are involved, but the correlation is solid. When the climate mode flips between El Niño and La Niña, the spin rate shifts in a way you can measure. That means major climate patterns are plugged directly into Earth's spin budget. But air is only part of the story. The oceans are an even more massive reservoir. They don't just sit there as a flat blue surface, they flow. Currents like the Gulf Stream in the Atlantic or the Kuroshio in the Pacific carry warm and cold water over thousands of kilometers at speeds of up to a meter per second, around 2 to 3 feet per second. That's slow compared to a car, but when you multiply it by depth, width, and length, you get an enormous moving load of water, sitting at particular latitudes, all rotating with the planet. A huge current running east-west at mid-latitudes is effectively a band of moving mass wrapped around Earth. If that current shifts position, speed, or depth, you've changed how much angular momentum is in the ocean versus in the solid Earth. Deep currents matter too, especially ones aligned roughly along parallels of latitude. Changes in those flows can subtly adjust Earth's moment of inertia. Just like with the atmosphere, if the oceans hold more angular momentum, the solid Earth can slow down a bit, and the day stretches. If the oceans give some back, the solid Earth can spin a bit faster. So here's the obvious question. If winds and currents are this important, can they explain the recent speed up by themselves, or do we still need the core and the moon in the picture? This is exactly what researchers test with their best models. They take atmospheric reanalysis data, which reconstructs past wind patterns and pressure from observations, and combine it with sophisticated global ocean circulation models. Then they calculate how much angular momentum is in the atmosphere and oceans at any given time, and how that should change the length of day. The good news is, this approach works very well for many features. Up to roughly 1 millisecond of variation in day length can often be reproduced by atmosphere-ocean models alone. Seasonal cycles, ENSO signals, and other climate modes all show up and match the real data quite closely. The bad news is, for people who like simple answers, that even these state-of-the-art models struggle to fully explain the anomalies we've seen since about 2020. When you subtract the modeled atmosphere and ocean contributions from the observed length of day series in these recent years, you still have a leftover signal. That residual is too big, and its timing is off if you try to blame everything on winds and currents. That's one of the main reasons scientists keep pointing back to core dynamics and mass redistribution in the deep interior as part of the missing piece. The atmosphere and oceans close a lot of the budget, but not all of it. Still, you shouldn't underestimate how tightly your daily experience is tied into this machinery. Every gust of wind you feel, every storm system that blows through, every blocking high-pressure system that stalls weather for weeks, all of that is part of the moving atmosphere whose angular momentum has to be balanced against the solid Earth. When you stand outside in a 50-kilometer-per-hour wind, about 30 miles per hour, you're feeling a tiny piece of a global system that can add or subtract microseconds from the length of the day. So now you have the full cast on stage: the moon and tides, the liquid core, melting ice, groundwater, jet streams, and ocean currents all feeding into micro changes in the rotation. That naturally brings up the next problem, which pushes things from quiet adjustments to weird behavior. If all of these systems are pushing and pulling, what happens to the actual orientation of the spin axis? Why is Earth's natural wobble, the Chandler wobble, suddenly acting strange in the same time window that the length of day has gone off script? Earth's spin axis is not nailed down in one spot, and lately its walk over the surface has started to look different at the same time your days are getting weirdly short. That's not a coincidence. When the way Earth wobbles changes, it tells you that mass is being moved around in a new way, and that feeds straight into the length of day problem we've been talking about. First, you need a clear picture of what this wobble actually is. Earth doesn't spin like a perfectly balanced, rigid top. The mass inside the planet isn't distributed perfectly evenly. The surface isn't smooth, and there are fluids moving around in the core, in the oceans, and in the atmosphere. Because of that, the point where the spin axis comes out near the North Pole wanders over the surface by a few meters every year. One component of that motion is called the Chandler wobble. It's a free oscillation with a period of about 433 days and an amplitude of a couple of meters at the surface. If you could draw the pole's position over time, it would trace out a tiny lopsided circle relative to the crust. Now, for the most of the 20th century and the early 21st, that Chandler wobble just kept going, like a background rhythm. Not perfectly steady, but always there with a certain size and period. Then, around 2015, something changed. The amplitude of the Chandler wobble suddenly dropped. Some researchers started calling this the diminished Chandler wobble, because one of Earth's natural rotational modes basically got damped down. The circle that the pole used to draw shrank. Why would that happen? You don't get that kind of damping for free. A wobble is a kind of stored energy. To shrink it, you need something that can absorb energy from the motion of the planet's rotation and turn it into something else, like heat or work done moving mass around. Recent work using GRACE and GRACE-FO satellite gravity data points a finger at hydrology and the cryosphere. In plain terms, changing water storage and melting ice. As ice melts from Greenland and Antarctica and as groundwater is pumped out and moved, the way mass is distributed on Earth's surface changes enough to interfere and damp the Chandler wobble. The wobble didn't just randomly calm down. The changing water and ice on the surface helped drag it down. That already tells you something important. The Earth's spin axis is not doing its own thing in isolation. It's being pushed and pulled by mass redistribution linked directly to climate and human water use. When you change how Earth wobbles, you're changing how mass is arranged relative to the spin axis. Remember the basic rule. For a given total angular momentum, if you put more mass farther from the axis, the spin slows and the day lengthens. If you pull mass closer to the axis, the spin speeds up and the day shortens. The Chandler wobble is literally a motion of the axis relative to the crust, which affects where heavy and light regions of the planet sit relative to that axis. So, when the wobble's amplitude suddenly shrinks, that means the system that trades and redistributes angular momentum between the solid Earth and its fluid envelopes has changed its behavior. Some models show that the post-2015 change in the Chandler wobble lines up with a shift in length of day trends. It's not a perfect match, and it doesn't completely explain the 2020-2025 speed up on its own, but it's another clear signal that something about Earth's rotational behavior entered a different regime around the same time. You have the liquid core flow evolving, the moon's tidal geometry doing its own cycles, the climate system accelerating ice melt and groundwater movement, and on top of that, the pole's natural wobble gets damped down. That's a lot of separate subsystems all showing noticeable changes in roughly the same decade. Because of that, scientists are now starting to treat the Chandler wobble and polar motion in general as climate sensors, not just curiosities in rotation theory. If the path and amplitude of the wobble respond to where water and ice are sitting on the planet, then tracking that wobble with high precision effectively gives you another way to monitor the state of the climate system. Mid-2020 studies are finding strong links between variability in polar motion and mass loss from Greenland, Antarctica, and shifting groundwater storage. In other words, you can see climate change in the way the pole drifts and circles over time, in addition to seeing it in temperature records and sea level data. Put all that together, and the simple idea of a day is just one spin breaks down. Earth's spin is not the motion of a rigid ball. It's the net result of several coupled systems: the solid mantling crust, the liquid outer core, the atmosphere, the oceans, the ice sheets, and the groundwater. They all exchange angular momentum. They all move mass around. They all affect both the speed of rotation and the orientation of the spin axis. A day is no longer just 24 hours. It's the integrated behavior of these subsystems vibrating, wobbling, and damping each other out. So when you hear that the Chandler wobble has weakened or that the pole's path has shifted direction, that's not just trivia. It means the balance between those subsystems has changed. It means some combination of climate forcing, core dynamics, and tidal interactions is now acting differently than it did a few decades ago. And that, in turn, helps explain why the models that used to predict length of day years in advance are suddenly being stressed by a run of record short days. Now that you can see the wobble, the pole drift, and the climate signal all tangled up with day length, the stakes on the timekeeping side should feel a lot higher. Because the next step is this: if Earth's spin is this messy and this sensitive, what happens when we actually have to change the global time standard to deal with it? What does it mean in practice if we really have to do something we've never done before and delete a second from the world's clocks? How do you even delete a second from every clock on Earth without breaking things? That's the problem timekeepers are now forced to think about. Because the same speed up in Earth's rotation that's shaving milliseconds off some days might push us into doing something we've never done before, a negative leap second. Up to now, leap seconds have always gone one way. Since 1972, we've added 27 leap seconds to Coordinated Universal Time, UTC. Every one of them was positive. On those days, clocks went 23:59:59, then 23:59:60, then 00:00. You got a 1-second bonus so that atomic time could wait for Earth's slightly slowing rotation to catch up. All the discontinuities have been add a second, never remove one. A negative leap second is the opposite. On that day, there is no 23:59:59 at all. Clocks would go 23:59:58 straight to 00:00. 1 civil second just does not exist. This has never happened in history. The standards allow it in theory, but nobody has ever actually done it. There's no real-world dress rehearsal, no last time we tried this incident to study. It would be the first deliberate deletion of a second from global time. That sounds like a neat trick, but for modern infrastructure, it's a nasty edge case. Most software and hardware was built under three assumptions. Leap seconds are rare, they are always positive, and many systems will never see one during their lifetime. A negative leap second breaks all three at once. Think about how much stuff depends on timestamps. Operating systems schedule tasks by time. Databases order rows by time. Financial exchanges match trades by time down to microseconds or nanoseconds. Logging systems assume time always moves forward by steps of 1 second or less, never zero, never negative. GPS, telecom networks, and aviation systems all assume that time is strictly monotonic. Each new timestamp is greater than the last. No gaps, no repeats. Now, insert a moment where 23:59:59 never happens. Any code that assumes every minute contains 60 seconds suddenly faces a minute that has 59. Some devices might try to repeat a second, some might smear the adjustment over a window, some might jump straight over it. If all of them do this differently, then comparing logs between systems stops being reliable. A trade executed according to one clock could appear to happen before an earlier trade according to another. In networks that depend on tight synchronization, that kind of inconsistency can cause timeouts, failures, or incorrect failover decisions. It's like pulling a rung out of a ladder while people are still climbing. We already know positive leap seconds cause trouble. Past insertions like the one in 2012 triggered bugs that crashed big websites and services because their software couldn't handle a repeated second cleanly. A negative leap second is worse because almost no code is written with missing second logic. Timekeepers can design a clean spec, but out in the wild, there are millions of devices and applications that will react in unpredictable ways. So when might this actually happen? Early projections, before we properly accounted for climate effects, suggested that if Earth's speed-up continued, a negative leap second might be needed as early as the mid to late 2020s. More recent analyses, including the 2024 Nature paper we talked about earlier, plus follow-ups in the technical press, now point to something like around 2029 as a plausible target, assuming the current acceleration trend persists and ice melt slowing delays it by a few years. To be clear, that date is not locked in. It depends on how length of day evolves over the next few years. If the core flow changes again, if the moon's tidal geometry shifts with climate-driven mass redistribution speeds up or slows down, the schedule moves. But late 2020s, maybe around 2029, is close enough that serious bodies, national metrology institutes, satellite operators, stock exchanges, are already modeling what a negative leap second would look like for them. They cannot wait until the last moment, get a 6-month bulletin, and then improvise. Now, layer on one more twist. Just as we're approaching a possible negative leap second, the world has basically decided to kill leap seconds altogether. In 2022, the General Conference on Weights and Measures, the top metrology authority, voted to stop using leap seconds by or before 2035. Instead of constantly forcing UTC to track Earth's rotation within 0.9 seconds, they'll let the difference between UT1 and UTC grow larger, possibly up to a minute or more over many decades, and then fix it with a rarer, bigger adjustment, or maybe by stretching a whole minute slightly so there's no single jump. The reason is simple. Leap seconds are causing more and more trouble in a world where everything is digital and globally synchronized. Each one is a discontinuity that has to be handled correctly in every system that cares about precise time. And the more we rely on automation, the higher the cost of getting it wrong. The recent speed-up of Earth and the resulting talk of a negative leap second just pushed that problem into sharper focus. It forced timekeepers to admit that trying to keep civil time perfectly glued to Earth's wobbly, irregular rotation with single patches is not sustainable. So you're in this strange corridor. On one end, there's the long-term plan. By the 2030s, no more leap seconds, just a slowly drifting UTC that occasionally gets a big, well-planned correction. On the other end, in the late 2020s, there's a non-zero chance that the first ever negative leap second will be needed before that new regime is fully in place. The result is a kind of race. Will Earth's spin demand a negative leap second before we successfully retire leap seconds altogether, or will the new rules arrive in time to dodge that bullet? Either way, the big picture is the same. A few milliseconds shaved off some days since 2020 just ended a half-century-old way of defining civil time. The entire leap second system, introduced in 1972 to tie atomic time firmly to the sun and stars, is now being dismantled because the planet's actual rotation is too messy for that model. Earth twitched. The long slowdown paused and reversed for a while, and that was enough to break our neat story about time flowing in exactly 86,400-second chunks. This is the moment where the abstract geophysics and everyday technology fully merge. The decisions made by international timekeeping bodies over the next few years will affect how every operating system, every database, every satellite navigation receiver on the planet handles the concept of a day. Whether we actually see a negative leap second or manage to dodge it, the underlying cause is the same. Earth's spin is not as stable as we pretended, and now that we can measure it to microseconds, we don't get to ignore that anymore. So here's the tension going forward. If we do end up deleting a second, and if Earth's spin keeps drifting in ways we can't perfectly predict, what's the real worst-case scenario? Not the science fiction stuff about people being flung off the equator, but the realistic limits of how far this can go before our systems have to change again. How fast could the spin increase? What would that actually do to us? And where is the line between annoying for GPS and fundamental constraint on how we run a high-tech civilization? So how bad could this really get if Earth keeps spinning a little faster year after year? Is there any point where you personally feel it, or is the damage all in the systems we've built on top of the planet's imperfect clock? Right now, the changes we're talking about are in the range of 1 to 2 milliseconds off a perfect 24-hour day. Even if that grew to 10 milliseconds, a hundredth of a second, your body would not notice. Your inner ear, your balance, your sleep cycle, they don't care about that kind of shift. Jet lag comes from your brain seeing light at the wrong local time, not from some tiny change in the length of a full rotation. The extreme disaster scenario people like to joke about, where Earth spins so fast everyone at the equator feels weightless and gets thrown off, would need something completely different. For centrifugal force to cancel gravity at the equator, you'd need a rotation period of around an hour and a half, roughly 84 minutes, not 24 hours. That's a spin up by a factor of about 17. Nothing we're talking about here. Tides, core flow, atmosphere, ice sheets, groundwater, the moon's orbit, all of them are linked through angular momentum exchanges. Your 24-hour day is the result of that whole negotiation, not a fixed setting. In the 2020s, that negotiation finally became visible at the level of our best clocks. Atomic time said one thing, the sky said another, and the difference was big enough to force changes in the global time standard. As our measurements get better, we will keep seeing these mismatches. Some we'll be able to model, some will still surprise us. The horror, if you want to call it that, is realizing that even with all our satellites and supercomputers, we're still chasing a moving target when we try to say exactly how long today is. And if the target is moving, that means something deeper. The models we used to rely on for Earth's rotation are too simple. The next step in the story is about rebuilding those models from the ground up, using every tool we have, quasars, lasers, satellites, and atomic clocks, to turn this messy, twitchy planet into something we can predict well enough to run a civilization on. The spin-up of the 2020s isn't just a glitch, it's a stress test of our entire understanding of Earth. How do you update a planet model in real time while the planet itself is proving you wrong? For a long time, we treated Earth's rotation like a smooth curve, gently slowing down with some regular bumps from seasons and tides. The 2020-2025 speedup blew that picture up. Now the data says very clearly you can't treat Earth like a rigid ball plus simple tides anymore. You have to treat it like a moving, leaking, vibrating machine. Old textbooks showed the length of day as a slow upward drift, with small, predictable wiggles. The main story was lunar tides breaking the spin, with a bit of atmosphere and oceans on top. That works for a first pass, but modern measurements from satellite geodesy, VLBI, and atomic clocks show something much sharper. The curve isn't smooth, it's jagged. There are jumps, accelerations, and shifts that don't line up with the old, tidy models. The cluster of record short days since 2020 is the clearest warning. Your model is missing pieces, and the real planet is more erratic than you thought. So how do we actually watch the spin at the level of microseconds and milliarcseconds? One tool is VLBI, Very Long Baseline Interferometry. Arrays of radio telescopes scattered across Earth point at distant quasars, billions of light years away. Those quasars are effectively fixed points in the sky. By measuring the arrival time of radio waves at different antennas down to trillionth of a second, scientists can solve for how Earth is oriented in space and how fast it's turning with very high precision. Add to that satellite laser ranging, where ground stations fire lasers at satellites with retroreflectors and time the light's round trip to picoseconds. That gives distances with millimeter accuracy. Combine thousands of these measurements with GNSS constellations like GPS, Galileo, and others, and you get an extremely tight 3D picture of Earth's shape and motion. All of that feeds into Earth orientation models, tables and equations that say, on this date, at this time, Earth's rotation angle is exactly this, and the pole is exactly here. The difference now is what has to go into those models. You can't just plug in a tidal term and a simple atmospheric correction and call it a day. To match the data, you have to fold in realistic fluid core flow, detailed hydrology, changing ice sheets, atmosphere-ocean coupling, and the moon's exact orbital configuration. The rotation model has become a full Earth system model, where the length of day is just one output. One of the frontiers is the core. We can't see it directly, but we can see its magnetic field at the surface and in orbit. That field changes slowly over time, a process called secular variation. By inverting those changes, you can infer patterns of flow in the liquid outer core. At the same time, you have the length of day record, which tells you when the planet sped up or slowed down by fractions of a millisecond. Put those together, and you get a powerful constraint. If your inferred core flow doesn't produce the observed LOD variations, your model of the core is wrong. The faster spin in the 2020s is basically the core leaving a stronger fingerprint. It tells you that the large-scale gyres of molten iron, thousands of kilometers across, are changing in a way you didn't fully capture before. That might mean different flow speeds, different coupling strength at the core mantle boundary, or changes in how magnetic and mechanical torques are shared. Either way, it's forcing a rebuild of those inversions. You have to assimilate LOD data and magnetic data together, not separately, to get a coherent picture of what the core is actually doing. This is why national time labs are suddenly part of Earth science, not just timekeeping. Institutes like NIST in the US, PTB in Germany, NPL in the UK, and their peers run some of the world's best atomic clocks. Their job, on paper, is to realize the second and distribute UTC. But to keep UTC aligned with Earth's actual rotation, they have to track UT1, length of day, and all the messy geophysics that goes into it. When these labs publish that there's, say, a 30% chance of needing a negative leap second in the next decade, they're not just talking about clocks. They're saying, our best physical model of Earth rotation has changed enough that this weird event is now on the table. So time labs have quietly become Earth observatories. Every comparison between atomic time and astronomical time is a measurement of the planet itself. Every adjustment to UTC is a public statement that something in the Earth system has drifted. The negative leap second discussion is really a side effect of a deeper issue. We're discovering just how dynamic the spin of our planet actually is, in real time. There's also a wider physics angle here. In cosmology, you're used to the idea that big parameters, like the expansion rate of the universe, change over billions of years. You never think of them as perfectly fixed. Earth's spin is the same kind of thing, but on a human timescale. You grew up with one day is 24 hours, as if it were a constant. Now the data is telling you, no, the rotation period is a variable shaped by processes you can't see. Core flows, tides, climate, even groundwater pumping, and it's changing fast enough that you have to redesign your time standard while you're alive. That's the jump in perspective. Day length is not just a human convention, it's a geophysical quantity, and right now, it's moving. Our models are playing catch-up, being rewritten to absorb every new piece of data from telescopes, satellites, and clocks. And as they get more complex, the big question stops being just what is Earth doing and becomes what does any of this mean for normal people who just want their GPS to work and their money to move on time? Because the next step in this chain is where it hits you directly. If the planet is this twitchy and the time standard is being rebuilt on the fly, what does that do to the systems you touch every day? Your navigation app, your bank, the plane you're sitting in at 900 kilometers per hour, roughly 560 miles per hour, trusting that it knows exactly where it is. Right now, the way Earth is spinning is baked into almost everything you use, and you usually never have to think about it. But as soon as the planet stops behaving quite the way our models expect, you start to see where that assumption leaks. Your GPS, your bank, your flight across the ocean, they all depend on us knowing to absurd accuracy exactly how fast Earth just turned. Take GPS first, because that's the easiest place to see how ruthless the numbers are. A GPS satellite sends a signal that travels at the speed of light, about 299,792 kilometers per second, roughly 186,000 miles per second. In 1 microsecond, a millionth of a second, that signal moves about 300 meters, around 1,000 feet. That means a timing error of just 1 microsecond between what your receiver thinks and what the satellite thinks translates straight into a position error the length of 3 football fields. Modern GNSS systems fight that in every way they can. They use multiple satellites at once, apply relativistic corrections because the satellites are moving fast and sitting higher in Earth's gravity well, and constantly pull in Earth orientation parameters that describe how the planet is spinning and exactly where the rotation axis is pointing. As long as Earth's rotation changes in a way we can predict and update, those corrections keep errors down to meters or less. But if the planet's spin becomes less predictable, if millisecond scale changes in day length start wandering outside what the models can forecast easily, those corrections have to be updated more often with tighter, more complex models. If you don't, the satellites are where they are, Earth is where it is, but your math is lagging behind, and the error budget starts to swell. You might not notice that driving to the grocery store, but surveyors, precision agriculture, and landing systems absolutely do. Now look at money. In high-frequency trading, firms buy and sell in microseconds. Some systems timestamp trades with precision better than 100 nanoseconds, a tenth of a billionth of a second. Regulations in many markets require that these timestamps are traceable back to UTC, the same official timescale that has to deal with leap seconds and Earth's changing spin. When a positive leap second happens and clocks repeat 23:59:59, some systems stretch the second, some insert it cleanly, some smear it over a longer interval. If a negative leap second ever hits and 23:59:59 simply doesn't exist, now every time server and every trading system has to agree exactly how to represent that missing second. If they don't, you can end up with trades that appear out of order when you compare logs from different venues. That's not a sci-fi collapse of the stock market, but it is a very real legal and financial headache. Regulators have to be able to reconstruct what happened, in what order, and who is responsible if something goes wrong. Then there's aviation and spaceflight. When you're sitting in a plane cruising at about 900 kilometers per hour, roughly 560 miles per hour, a position error of a few hundred meters is usually tolerable. Onboard radar, visual separation, and air traffic control give you layers of safety. Still, the navigation systems that planes use, GNSS, inertial guidance, radio beacons, are all tied back to Earth-fixed reference frames that depend on knowing how the planet rotated between two times. Millisecond level errors get averaged out quickly, but if the underlying Earth orientation parameters are off and not updated, the navigation solution slowly drifts. For spacecraft, the tolerance is lower. When you do a gravity assist around Earth or a precisely timed engine burn, you're relying on the transformation between an Earth-fixed coordinate system and an inertial frame that assumes you know exactly how far Earth rotated between two instants, down to tiny fractions of a degree. A 1 or 2 millisecond error in day length translates into a small but real shift in angle. Over interplanetary distances and at speeds of tens of kilometers per second, that angular error multiplies into a path difference you cannot ignore. So as Earth's spin behavior gets more noisy, mission planners have to fold more frequent and more detailed rotation corrections into their navigation pipelines. Telecom networks and power grids are in the same game, just in a different way. Large telecom systems need clocks in different cities synchronized within microseconds to route data efficiently and diagnose problems. Power grids rely on precise timestamps to detect faults, coordinate protection systems, and maintain stability over huge areas. If a disturbance hits the grid, engineers look at the timing of events at different substations to figure out where it started and how it propagated. All of that assumes time is a simple, monotonically increasing coordinate, with occasional, well-understood corrections. As soon as you introduce negative leap seconds or more frequent adjustments, every piece of infrastructure that assumes time never skips has to be audited. Time distribution protocols, logging systems, fault analyzers, they all have to be checked and sometimes redesigned so they don't crash or give misleading answers when a second is skipped, stretched, or handled differently than before. Now, zoom back down into your pocket. Your smartphone, quietly syncing over the internet to NTP servers or locking onto GPS time when it can, is sitting on top of this whole stack. Behind that simple lock screen clock is a global relativistic timekeeping infrastructure, atomic clocks in labs, satellites broadcasting time codes, observatories measuring quasars, the IERS publishing Earth orientation parameters, and standards bodies deciding how UTC will behave when Earth's spin does something odd. When you tap your screen and see 1403, you're not just reading a number, you're touching the front end of a planetary scale experiment. Can we keep a global digital civilization aligned to a planet whose rotation is not perfectly stable? The recent speed up, the talk of negative leap seconds, the decision to end leap seconds by 2035, all of that is stress testing that experiment. And here's the key point for the rest of this story. This entire high-tech stack is being pushed around by processes that have been running for hundreds of millions of years. Tides, core flow, climate shifts, all of that was changing day length long before we built satellites and stock markets. We're just now precise enough to feel it. So if you really want to understand how weird it is that your day is shrinking by milliseconds, you have to look backward to times when days were much shorter, years had more days, and no one was around to worry about leap seconds. Because once you see how much Earth's day has changed since the age of dinosaurs, these modern millisecond tweaks stop looking like noise and start looking like the latest chapter in a very long story. You're used to a 24-hour day like it's built into the universe. But for most of Earth's history, that number was different. During the time of the dinosaurs, the planet was spinning noticeably faster, and the day would have felt shorter even though the year, the orbit around the sun, was basically the same length it is now. We know this from fossils, not from guesswork. Certain corals and shell-forming organisms laid down growth bands in daily and seasonal cycles, like a very fine-grained calendar. In late Cretaceous fossils, roughly 70 million years old, you can count how many daily bands fit into one yearly cycle. The answer is about 372 days in a year. Same year length, more days. That means each day was only about 23.5 hours long, around half an hour shorter than your current day. Over more than 100 million years, tidal friction has been steadily stretching that day. The moon pulls on the oceans, the tides drag against the sea floor, and energy is drained from Earth's spin and passed into the moon's orbit. The net effect is small each century, but it adds up. Your 24-hour day isn't some cosmic default. It's just where the Earth-Moon system happens to be right now in a long, slow evolution. You might think, fine, that's deep time, that's fossils, but can we actually see this trend over human history with numbers we can check? Yes, and the evidence there is surprisingly concrete too. Ancient civilizations tracked solar eclipses very carefully. People in Babylon, China, Greece, and elsewhere wrote down where and when they saw the sun go dark. Those records go back a few thousand years. Today, we can compute exactly where eclipses should have been visible using precise orbital mechanics and our best models of the Earth-Moon-Sun system. When you align the ancient reports with the modern calculations, you find small mismatches unless you allow Earth's rotation to have been slightly slower today than it was then. Over the last 2,000 to 3,000 years, the best fit is that the average day length has increased by roughly 1.4 milliseconds per century. That lines up with the tidal breaking story. Tiny changes per century, but they're real, and they're measurable in both fossils and historical records. So we have a slow, smooth trend from both very old rocks and relatively recent history. But the 2020 to 2025 spike of shorter days isn't smooth at all. Where do those jagged anomalies fit into this picture? When scientists build long-term models of day length using all available data, fossils, eclipse records, modern telescopes, satellite tracking, they see more than just a straight line. On top of the steady tidal trend, there are long-period oscillations, including one with a timescale of roughly 1,500 years and an amplitude of a few milliseconds. That means over about 1,500 years, the length of day can swing up and down by several milliseconds relative to the long-term trend. Those multi-century wiggles are thought to come from slow changes in core flow, mantle dynamics, and large-scale climate patterns. We're only resolving them clearly now because our clocks and space geodesy tools are precise enough and our records are long enough to see them. So the anomalies between 2020 and 2025 might be one sharp part of that longer period variation, sitting on top of the tidal slowing and all the shorter-term stuff from atmosphere and oceans. In other words, this weird decade could be one crest in a 1,500-year oscillation that no human civilization has ever measured until now. So if the day was about 23.5 hours at the end of the dinosaur era and roughly 24 hours now, where does this go in the very long run? If you project the average tidal slowing forward, not worrying about all the shorter-term ups and downs, you get days that are about 25 hours long several 100 million years from now. That's not next century, that's deep future, but it's a real consequence of the same physics that's giving you millisecond shifts today. A longer day means fewer days per year, different tidal patterns, and shifts in climate rhythms that depend on the day-night cycle. Even satellites that are locked to Earth's rotation, like geostationary orbits, would have to adjust to a different spin rate and different Earth-Moon distance. So what you're seeing now, the planet shaving or adding milliseconds from one year to the next, is the microscopic beginning of that macroscopic story. The underlying trend is slow, but it never stops, and the short-term swings ride on top of it. Your 24-hour day is a temporary state in a much longer evolution of the Earth-Moon system. So what does that say about a day as a unit, the thing you build your schedule and your entire sense of time around? From cosmology, you already accept that space-time isn't static. The universe expands, the expansion rate changes, cosmic structures grow and move. Geophysics is telling you something similar on a smaller scale. Day length is not fixed either. It's a geophysical quantity controlled by tides, core flow, climate, and orbital mechanics. Put those two ideas together and the day stops looking like a fundamental constant and starts looking like a local, time-dependent parameter. Our clocks, with their clean equal seconds and 24-hour cycles, are just labels we stick onto that moving target. We adjust them with leap seconds, we debate negative leap seconds, we decide when to stop tying civil time to the sun so tightly, all because the thing we're trying to measure, Earth's rotation, refuses to hold still. And that leads to one last crucial question before we wrap the story. If all of this rests on tiny changes in day length, how do we actually measure those milliseconds with enough confidence to blame the core, the moon, the climate, and ourselves? How do we know it's not just instrument noise? The answer is that we've built an entire layer of technology purely to watch Earth spin, and it's those instruments that prove this speedup is real. Right now, people are telling you that Earth had a day that was shorter by 1.5 milliseconds, and you're supposed to believe that's real, not just a rounding error. So the obvious question is, how do we actually measure something that small and be sure the planet really sped up instead of blaming a glitch in one machine? The answer is, we don't trust any single instrument. We built an entire stack of independent systems that all watch Earth in different ways, and then we check that they agree. Only when radio telescopes, satellites, lasers, and atomic clocks all point to the same answer do we say, yes, this day was shorter by about 1.5 milliseconds. Start with the most direct way to see Earth turn against the sky. Very Long Baseline Interferometry, VLBI, links radial telescopes spread across whole continents. These telescopes all point at the same distant objects, usually quasars billions of light years away. Those quasars are so far and so stable that for our purposes, they're fixed reference points. A radio pulse from a quasar hits one telescope first, then a fraction of a second later hits another telescope thousands of kilometers away. By recording the signals and comparing them, you can measure the time difference between antennas to trillionths of a second. That time difference depends on the exact orientation and rotation of Earth at that instant. If Earth has rotated a tiny bit more or less than expected, the pattern of arrival times shifts. By doing this every day with many telescopes and many quasars, scientists solve for UT1, the Earth against the sky time. They get the rotation angle and the position of the pole with crazy precision, down to microseconds in time and micro-arc seconds in angle. That gives you a direct geometric measure of how fast the planet just turned, completely separate from atomic clocks. Now add another layer, satellite laser ranging and GNSS. Ground stations shoot very short laser pulses at satellites that have retroreflectors on them. The light goes up, reflects, and comes back. You measure how long the round trip takes, down to trillions of a second, and that gives you the distance to the satellite to within a few millimeters. Do this from many stations to many satellites over and over, and you build up a precise 3D picture of where those satellites are relative to the Earth's surface. GNSS constellations like GPS, Galileo, and others add even more information because their orbits and broadcast timing depend on Earth's gravity field and rotation. The combined dataset tells you not just where the ground stations are, but how Earth's shape, gravity, and spin are changing. If the rotation rate changes, the ground stations move under the satellites slightly differently. Over days and months, that shows up as tiny but consistent shifts in the satellite tracking data. So now you have a second independent way of seeing changes in length of day, in the geometry of satellite orbits and laser ranges. Then there are the clocks themselves. National labs run the world's best atomic clocks, including optical lattice clocks and advanced cesium fountain clocks. These devices are so stable that over long averaging times, their frequency error can be as low as 1 part in a billion billion. In more normal language, that's like measuring the age of the universe and getting it right to within about 1 second. Hundreds of these clocks spread across different countries are compared using fiber optic links on land and satellite links over long distances. From those comparisons, timekeepers build International Atomic Time, TAI, a kind of average of the best clocks on Earth. Coordinated Universal Time, UTC, is then derived from TAI, with leap seconds added or, in the future, possibly removed. The key point is that these clocks don't care how Earth is rotating. They are blind to the sky. They just tick at their own fixed atomic rate. That gives you a baseline timescale that is as smooth as we know how to make it. When you compare UT1 from VLBI to TAI from the clocks, any drift between them is Earth's rotation changing. All of this gets pulled together by one central service, the International Earth Rotation and Reference System Service, IERS. They are the ones that take VLBI data, satellite laser ranging, GNSS, and other tracking systems like DORIS, and fuse them into a single consistent model of Earth's orientation and rotation. From that fusion, the IERS publishes Earth orientation parameters: how much Earth rotated today, where the poles are, how much UT1 differs from UTC, and how length of day is varying. These are the numbers that observatories, space agencies, GNSS operators, and atomic clocks all use. When they say, on this date, the day was shorter by 86,400 seconds by 1.5 milliseconds, that's not a rumor pulled from one sensor. That's a conclusion from an entire global network all agreeing. Radio telescopes looking at quasars, lasers pinging satellites, GNSS signals, and atomic clocks all tell the same story. Earth really did spin faster on those days. What you're watching here is precision physics operating at its limit. We're using cosmic radio sources, nanosecond-level satellite timing, and clocks that barely drift over the age of the universe to track changes in Earth's spin that are smaller than a blink by a factor of 1,000,000. The fact that these independent systems line up is exactly why scientists are confident that something real and global is happening to the rotation, not just to our instruments. And that brings the whole arc together. Once you accept that the measurements are solid, you're forced back to the physical causes: the moon, the core, the atmosphere, the oceans, the ice, and even human activity. Which leaves one last piece to talk through. And it's not about the planet, it's about you. If your day length is not fixed, if your clocks are constantly negotiating with a restless Earth, what does that say about your place in this whole setup? And how should you think about time on a world that won't stop changing its spin? You grew up on a simple rule. A day is 24 hours. Full stop, no discussion. But everything you've just seen says something different. It says that 24 hours is just a human label we slapped onto a rotating, wobbling, climate-shifting rock, and the rock does not care about that label at all. We tried to nail the concept of a day to 86,400 seconds, and now we're arguing about negative leap seconds because the planet refused to stick to the script. The fact that we even have to talk about deleting a second from global time is your proof that one day is a convention, not a fundamental constant. Once you see that, your view of our entire civilization shifts a bit. Almost everything we rely on assumes a bunch of background numbers stay basically fixed. Gravity is constant enough, sea level sits where we built our quartz, day length is stable enough that we can define time, build schedules, and sync machines across the planet. But Earth quietly violates those assumptions all the time, just not in ways your body can feel. It shifts sea level by millimeters per year, moves the poles by centimeters to meters per year, changes day length by microseconds to milliseconds, and we only notice when those tiny shifts poke holes in the systems we've built. The 2020 speedup is exactly that kind of warning. It doesn't throw cars into the air, it does something more subtle and more dangerous from a systems point of view. It exposes that our planetary scale infrastructure is sitting on top of a dynamic geophysical engine we only partly understand. We designed GPS, high-frequency finance, global telecom, and satellite navigation as if the background rotation of the planet was smooth and predictable. Now the data is saying, no, it twitches, it accelerates, it slows, it responds to tides, core flows, climate, and even groundwater. And if you don't track all of that, your stable foundation isn't actually stable. The strange part is, this is also a massive scientific opportunity. By measuring microsecond-level changes in day length, we are not just doing some nerdy timing exercise, we're probing the entire Earth system at once. A few microseconds off here, a fraction of a millisecond there, and you get clues about how the liquid core is flowing, how much ice has melted, how the oceans are shifting heat and mass, how the atmosphere is storing and releasing angular momentum. You turn the planet itself into an experiment in angular momentum and fluid dynamics. You're watching a metal ocean 2,900 kilometers down move just enough to tug on the crust. You're watching ice sheets lose mass and water spread toward the equator, slowing the spin a little. You're watching winds and currents shift as climate patterns like El Niño flip phase, and you see all of that reflected in the clock. That's an insane amount of information hidden in tiny timing differences that your eyes and ears can't detect at all. And this isn't just about Earth. In exoplanet science, we already estimate rotation periods of distant planets by seeing how their brightness changes over time as they spin. Dark and bright regions rotate in and out of view, and from that pattern, you get a rotation period. But now, with what we've learned here, you can go further in principle. If an exoplanet has large internal oceans, or a molten interior decoupled from its crust, or strong tidal interactions with a nearby moon, its rotation period might not be perfectly stable either. On those worlds, day length could also wander by milliseconds or more, driven by internal and external dynamics. We can't measure that level of detail for exoplanets yet, but the physics doesn't care about our current telescope limits. The same rules apply. What we're learning from Earth's weird spin-up becomes a template, a reference case for how rotation, tides, climate, and internal structure interact on any rocky planet. When we see hints of variability in a distant planet's rotation someday, Earth will be the baseline we use to decode that signal. So what does this say about your place in all of this? It says that the thing you treat as the most basic rhythm in your life, the 24-hour day, is actually the output of a negotiation between space and geology. The moon pulls on the oceans, the core shuffles molten metal, the atmosphere pushes with winds, the ice sheets melt and move water, and the planet's spin responds. We then take that messy, constantly adjusted rotation and try to slice it into clean, equal seconds so that our phones, planes, banks, and satellites can agree on what now means. You're not outside that process, you're inside it. Every time your phone syncs its clock, it is listening to the outcome of that negotiation. Every time a leap second is added or debated, that's the human layer reacting to a change in the planetary layer. You're living in a world where tiny differences in how the core flowed this decade versus last decade can affect when an international body decides to tweak the definition of civil time. And that brings you back to the core idea of this whole story. A day isn't sacred. It isn't guaranteed. It's just the current behavior of a spinning, wobbling planet under the combined influence of tides, magma, ice, and air and orbital mechanics. In the deep past, days were shorter. In the distant future, days will be longer. And right now, in your lifetime, those changes have finally become visible at the level of the best clocks we've ever built. So the next time someone says there aren't enough hours in the day, you can answer them literally. You can say, you're right, there are actually fewer milliseconds than there used to be. Earth is spinning faster. Our days are not sacred. They're the emergent behavior of tides, magma, ice, and space. And you're here, right now, while the planet quietly rewrites what a day means. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.